Good morning, everyone. Welcome to the first plenary lecture, and it will be presented by Professor Wei Chen. My name is Wing Liu from Northwestern University, and I'm chairing these sessions. Professor Wei Chen is the Wilson Cook Professor in Engineering Design, and she is also the chair of the Department of Mechanical Engineering at Northwestern University. She's my boss, She is the internationally recognized for her contribution to design under uncertainty, for which she was elected to be a member of the National Academy of Engineering in 2019. She currently serves as the editor-in-chief of the ASME Journal of Mechanical Design and also the president of the International Society of Structural and Multidisciplinary Design. In the past, she served as the chair of the ASME Design Engineering Division. She is also this year's recipient of the ASME Pi Tau Sigma Charles Rules Richards Memorial Award this year, 2021, which is presented to an engineering graduate who has demonstrated outstanding achievement in mechanical engineering 20 years or more following graduation. Professor Chen is one of the most cited researchers in the field of engineering design. In addition, her methods have been integrated into quite a few commercial software, such as the EyeSight from the 3D system and the HyperWork from the hotel engineering. Throughout her work with many researchers in different disciplines, Professor Chen has done an impressive impact in a design researcher big across multiple fields, and you'll be hearing about it. Today, she will present to us her interdisciplinary research on data-driven design of engineering material systems. Now, before I turn over to Professor Wei Chen, for the audience, as you're watching this talk, if you have a question for Professor Wei Chen, please use the Ask tab. Okay, and the Ask tab, actually, you need to specify the first name, which is Wei, and the last name, which is Chen. Okay, on the left side bar of the platform. And if there's time, your question will be addressed. Please welcome Professor Wei Chen.
Wayne, thanks so much for your kind words, and thank you for everyone for joining this talk. I feel truly honored to speak about design research in this flagship mechanics conference. I'd like to thank Wing and other mechanics colleagues who have collaborated with me and teach me mechanics during the past decade. Fearing that things may go around with the live talk, and also encouraged by the conference organizers, I have pre-recorded my talk, but will answer the questions in person after the talk. So let's go ahead to play the talk video now. It is my pleasure to give this talk on data-driven design of engineered material systems. In this talk, I will share with you my views on the challenges and opportunities in this area. I acknowledge that this is really the work I'm presenting here is really a joint effort between my group and many other groups in materials, mechanics, manufacturing. And I'm listing here some of the colleagues I have been working with in the past years. So to put this topic into context, I'm showing here some examples of the material systems that we have been working on. These range from soft material system like polymer to hard material system like microelectronics and additive manufacturing. But one thing they shared in common is that all these functional materials are fabricated at nano and the micro scale level by combining material constituents in certain structured way to achieve superior property and performance. So structure design is a big part of the material design. As I'm showing here, for the organic photovoltaic cells, you can see that we can design the surface pattern, and we can also design the microstructure in the sandwich layer to achieve optimum transportation behavior. There are many challenges in designing very complex material system, and I'm using two examples to illustrate the challenges. So what you're seeing here is that this is a CFRP composite structure, achieve very lightweight and also have to have very strong endurance. And from the design perspective, you can see that there are design decisions range from nanoscale in terms of what epoxy to choose to mesoscale level, like the composite layer structure architecture, all the way to the macroscale level, like the topology of the vehicle structure. Due to the manufacturing process impact, we can see that the material behaviors are very heterogeneous at different locations. So there's heterogeneity, and the materials are spatially and temporally varying in terms of their structure and the properties. So when we talk about the material loss, if we take into account heterogeneity and the stochasticity, and we have to take into account uncertainty. So there are associated with this is the multiscale computational complexity. Oftentimes, using the computer model itself is not sufficient to predict the behavior. So we have to combine also the data from the experiment to calibrate our model for better prediction. Similar challenges also exist in another example I'm showing here is additive manufacturing. So as you can see here, that why there are many advances in the past years simulating the AM process from process to structure to property behavior. On the other hand, the integrated design of process and structure is still in its infancy due to the many challenges that very similar to the composite system I talked about earlier. There's stochasticity issue, there's information heterogeneity issue, there's multiscale complexity and location dependency. Finally, the nonlinearity adds another layer of challenge to prediction as well as optimization. So associated with this is that there are several new paradigms has emerged in recent years to handle this kind of challenge, and the ICME is one of those paradigms. It's really a very interdisciplinary approach by integrating data science, material modeling, and the manufacturing into design and also deploy of the material into systems. So this notion of combining data from different sources is also echoed in another initiative called the Material Genome Initiative. As you can see here in recent years, there's a strong interest in collecting the data not only from just the lab experiments, but also to the real life operation. So that's the concept of digital twin that comes in that really try to promote the use of data from various sources we call multimodal data integration to accomplish the goal of design as well as for accurate prediction of the behavior. So if you think about the data flow, you can use this diagram that my colleague Greg Olson had developed that shows that there's really a map between processing to structure to property and all the way to performance. While material scientists have been working heavily in predicting the property, the people in mechanics actually care more about performance. And that's a much more difficult problem because here we need to take into account really the geometry, the part geometry. And this is called forward prediction. On the other hand, design is really an inverse process that you start with some goal, then you identify the optimal solutions in these different domains. And adding to this complexity is that for material system, we also need to consider the possibility of different material constituents. So that's really a combinatorial problem, which really increased the challenge in design exploration. There's actually a concentrated effort in creating data resources for data-driven design. So I'm using an example that myself have been involved in a NS project, CSSI project with other 5 different faculties. And the data resource is now called the Material Mine. And our goal is to expand a polymer nanocomposite database to Metamaterial database. And there's a lot of communication in this process between the computer scientist and domain scientists to develop the right knowledge graph and the ontology, the data schema, and so on. But fundamentally, there's always a question about what is the right design principles that guide all these activities. So data-driven design, data-driven material design is also by itself now a very interdisciplinary field. And what I'm showing here is that it really involves the interaction between design, mechanics, materials, and also manufacturing, why the data science is sitting at the core. Why there's this very strong increasing interest in using methods such as deep learning, there's always a question about what are exactly the new capabilities, right, added by these fancy methods. So are we reinventing the wheel by developing these techniques, or are there any new capability that this method adds to the existing computational algorithms? Why deep learning has been widely used now in imaging analysis and some other analysis is always a question about what is a relative role, what are the relative roles that conventional statistical methods play, for example, regression methods, Gaussian process model, and so on, that we have been used for many years. And finally, I think it's always interest about whether really deep machine learning really help us to learn. So here is the question about whether the results can really provide a physical understanding, better physical understanding. So hopefully my talk today can shed some light on some of the answer to these questions. So I'm going to mainly focus on the design from the design perspective. How do we address this topic? On the other hand, I'm sure in this conference, there will be a lot more talks on how do we use data-driven methods for the other topics like mechanics, manufacturing, and materials. So from the design perspective, we really have three core subjects here: design representation, design evaluation, and the design synthesis. So sitting in the middle is this database that kind of cover different domains of processing, structures, and property. And in design representation, the question we really want to address is how do we extract from this database the minimal number of design variables that can fully represent the things we can control, and we call them control factors. And these design variables can span from the domains such as like SMILES, which represents the chemistry design, to material composition, to morphological design like correlation function, and all the way to the large structure like topological geometry. So all those can be used as design variables. In the design evaluation domain, and we're working with very expensive physics-based modeling and simulations such as molecular dynamics simulation, DFT, and finite element analysis. So the question here is how do we build a surrogate model for fast analysis, and in the process maybe also integrate with the physical data to do calibration and validation. Once design evaluation creates the model, now the question is how do we do design synthesis? So here the question is really how do we quickly explore the design space using methods such as genetic algorithm, deep learning, and Bayesian optimization, considering the constraint and the bounds in the process. These three topics are very interrelated, and that's something that I want to show you in this talk is some methods we developed. For example, between design representation and design synthesis, we're developing methods that can address multiple, we call mixed variable case. Qualitative can be categorical variables and a quantitative variable that are continuous. In the between the topic of design representation and design evaluation, we're looking at methods that can handle different length and time scale phenomenon. And finally, between design evaluation and design synthesis, there's a question about how do we quantify the uncertainty, how do we take into account the noise, as well as the computational cost. So in the remaining part, I'm going to go over each of these three topics and show you some representative work. In design representation, one big topic is really the subject of microstructure characterization and reconstruction. We call this MCI. This is important topic because we want to expand the design to the material design domain, which means we have to model the microstructure behavior from the lowest scale level. Here is the case that we use image, start with image, we extract information from there, that's called characterization. Then we build the statistically equivalent reconstruction. Those are the digital models of the microstructure that can predict material behavior. So here I show that some of the behavior may involve very large amount of uncertainty. And that brings up the need that you need to do really reproduce or this so-called statistical equivalent images for analyzing the property. There are really two major categories of methods in this, in this topic. One is called the deterministic representation. Another one is stochastic representation. So deterministic representation is the one that really goes well with method like topology optimization. So here you decide each unit cell, like each actually unit, whether it should be black and white, whether you should place material, not placing material. So from the design perspective, it's very high dimensional design space. So it's very expensive problem. And from the manufacturing point of view, you need to use top-down manufacturing process like 3D printing in order to achieve the design exactly. On the other hand, the statistical representation is more friendly for like mass production processing methods, because here it recognizes that material systems are heterogeneous and stochastic. On the other hand, they follow some patterns. So in the past years, we have looked at many different methods, ranging from simple approach like descriptor-based method that can model very well the regular geometry, to functional-based methods such as correlation function, as well as deep learning-based method that really can model very complex morphology. Here is like a polymer, copolymer case. On the other hand, these methods, some of those deep learning methods do lack of physical understanding, because the latent even you can derive latent variable from there, they will not be, you won't be able to relate them to the physical processing conditions easily. So I want to show you in our research, we actually has evolved from the deterministic approach to the more stochastic approach for nanomaterial design. So here is an example. It's a solar cell design example that we designed the surface pattern and to achieve light control, which is measured by the energy absorption here. So initially we used the topology optimization method, which is a deterministic representation. So we used SIMP method, level set method, the genetic algorithm to optimize the structure. And you can see that we actually achieved very good property here in terms of this is the band gap throughout the different wavelengths. So imagine during the day you have the sunlight may coming in different angles. So this is optimized, this structure is optimized for the whole spectrum of behavior. And in some cases, some wavelengths, you can see that it can be achieved almost to close to 100% light absorption. And also the fabrication validate that. So there's a red curve here, which shows the fabricated sample, and it match quite well with the theoretical results, which is the blue curve here. But what we found the problem with this kind of approach is that if we're using like a nanolithography to fabricate this sample, that it takes almost a week just to pattern a 4-inch wafer. So this kind of process is not going to be applicable for mass production or real engineering. So that makes us to think about different approach, and we will inspired by in the optical physics, there's actually a representation called the spectral density function that can transfer a very complex structure morphology through the Fourier transformation. It can transfer it into a very simple representation called SDF, spectral density function here. So you can see that here we only care about, in this curve, we only care about the lower bound and upper bound of this step function, which is also represented kind of corresponding to this ring shape, the inner circle and outside circle. This kind of representation offers a much more like a reduction. It's a huge dimension reduction from complex morphology to a step function, which is really good news for design, because now we are able to only design few parameters to accomplish a very complex morphology. So here I show you some example with different material system like particle system, the channel-like material system morphology. And you can see that each of them, I'm using some biological example here that we observed very similar behavior, like for a particle system like this, the spectral density function is a peak value. You can see that in terms of the feather color of a bird, it's going to be pure blue color. And it's also interesting to see that different kind of structure can accomplish the same goal. So this really reminds us that design is not really one-to-one mapping. One like a desired solution here, the spectral density function here could be actually accomplished by many different kinds of material system. On the other hand, you can see that this Gaussian-like spectral density function corresponding to that, the material behavior, the structure is very aperiodic, almost there's no pattern underneath that. And you can see that the corresponding color is actually a white color. This is approach that we call the physics-aware design representation. It allows us to map structure to property easily. It actually also helps us to create a relationship with processing very easily. So you can see here, I gave 3 examples. The samples are made by different process like focused I-beam, phase separation, nano wrinkling. And you can see that for each of those different sample process, there's a very different spectral density function behind that. So this is almost like a signature of a process. And we can see that, these can be also lead to different properties, like each of those spectral density function can lead to different properties at the end. So using this SDF concept as a link, we actually demonstrated that we can do concurrent process and the material design together. So this is an example that I worked with Terry Oden's group a couple of years ago, and the paper is published in PNAS on designing a nano wrinkling structure to accomplish a very good solar cell behavior, which is the energy absorption. So that the nano wrinkling is created by a process that you can think about this as like to take advantage of the buckling behavior of the material and create wrinkles. But this is always a question about like how dense, right, this wrinkle should be. And to represent the design space, we actually look at the many samples from Terry's group and then find that underneath that, doesn't matter, how you change the process condition, there's a very common SDF function form they share, which is a Gaussian model here that we only need to design the peak value as well as the dispersion, the variance of this curve, and then we are able to control different properties. And we also find that those parameters like the lambda, which is the reciprocal of the peak value here, this is the wavelength, can be related to a single processing parameter. This is the reactive ion etching time. And on the other hand, the other processing condition like O2 etching time can control the volume fraction F, and the directional real time can be used to control the thickness. So by creating this kind of one-one correspondence between the processing condition as well as the structure variable, we are able to do concurrent optimization for both the processing as well as the structure parameters. And our design is also validated and by fabricating it and then actually physically validating the behavior. So the spectral density function approach that I talked about here is a very good method to capture some of the complex behavior. On the other hand, it's still considered as a low order from the point of view that this is equivalent to like a 2-point correlation function. So to capture the higher order correlation, we need to use either higher order correlation function or better approach. So here I'm showing you a deep learning method that we actually use a transfer learning concept that this is a library built, it's called the VGG19 library. It's pre-trained on objects like cats and the dogs. But using the neural network built by this object, we could actually reconstruct very complex morphology using only one single image. So the original microstructure here, I show you an example that original structure. This is from, I think it's a kind of concrete material. You can see the reconstructed behavior. It's very close to the original in terms of this statistical characteristic. And we also demonstrate this to a very difficult problem. This is a copolymer problem. It's almost like a fingerprint that this is the original one and this is the reconstructed one. We tried this method on using many other methods such as correlation function and descriptor-based approach. None of them can be useful for such complex morphology. So for people who are interested in this subject, I would highly recommend recommend that you take a look at this review paper we published in the Progress in Material Science, where we reviewed these different methods I just mentioned, and we looked at their performance, either plus or minus, from the point of view of whether they can handle irregular geometry, what is the reconstruction speed, and whether they can handle multiple phase, not just a two-phase material, and whether they can take information from 2D to reconstruct 3D images. And finally, from the design perspective and ease to relate to the manufacturing process condition, and we're looking for whether they are physically meaningful. So you can see that the different methods, have very different characteristics. And so based on your problem of interest, you may pick and choose different techniques. So why the MCR subject, the reconstruction characterization subject, seems to be a little bit more material science and maybe processing oriented. I want to now talk about a topic maybe more relevant to the mechanics people here, which is called design evaluation. And design evaluation is a subject that really covers the goal to map relationship between processing to structure, to property, and then to performance, so the PSPP chain. Here I'm listing here some very representative machine learning techniques have been used by different application and different works, and they range from statistical inference method like Gaussian process model to neural network to more recent technique like VAE and GAN. As you can see here, when you have more sophisticated machine learning technique, you can handle more complex inputs such as material like a microstructural morphology, chemistry definition that may involve very long chain of smiles or graphical representation. And we can use very traditional approach to feature identification and dimension reduction. On the other hand, we can also using deep learning methods to really derive the latent representation of those different complex inputs. So there are many subjects in this category, and I'm not able to touch all of them, but I'm going to focus today more on how we use methods for big data, small data, and the mixed variable problem, which is a new technique we call the LVGP, latent variable Gaussian process method that we developed. And I will demonstrate that this method can be very useful for material design across different scale levels. So big data is really a case where we benefit from offline simulation and then use it in the real time. We call it online, like multiscale prediction. So here is example that we worked on just I think 2 years ago. It's also a joint effort between several different groups that we're really looking for, we call the path-dependent behavior, like hyperelasticity. So here, what you see here is that this, depending on how you go from one point to another point, the boundary condition, which is the strain input, can be quite different. And though this is something very useful for predicting nonlinear plasticity behavior. Here, if we look at the model, the stress is a function not only of the current state strain, but is also a function of the past history in terms of the strain, in terms of the stress, as well as M stands for microstructure morphology and the P stands for constituent properties. So in order to handle this almost like a sequence of data across different time steps, we demonstrated that we could actually use, we call the recursive neural network to build a sequential deep learning model. So here we actually did about 15,000 samples, created the 15,000 samples that we use Gaussian process to simulate very complex load paths. So all this line here, the blue, red, green curve represent different load paths. And we also considered a very different morphology for the microstructure. And for used finite element simulation and the data, this amount of sample, we could actually create a very accurate recursive neural network to predict any kind of loads and any kind of microstructure morphology. So here basically it shows that the dots are the prediction that match very well with the dots are the real evaluation, and that the curves are the prediction, and they match extremely well. And using such neural network model, it's a recursive neural network model, we could actually identify the yield surface evolution and the loading. And in the past, many people use experiments to identify such yield surface. And here we can use computer simulation to identify such surface from very different microstructure. So this work is again a joint work that has been published in the PNAS. So that's where really the big data can play a role. And once we have created this kind of model, material behavior model, we can use it again in real-time multi-scale simulations. On the other hand, we also have many cases that we do not have a lot of data. And this is especially true when our evaluations are finite element based and or molecular dynamic simulation. So a very useful approach here is called the Gaussian random process, which I will show that we have also expanded this method to be more powerful for mixed variable problem. So to illustrate the essence of this method, you can see that when you collected some data points, you could actually have many different ways. The green, red, and the blue curve, they pass these points, right, in different ways, which means there's uncertainty in the prediction. Traditional neural network method can give you uncertainty prediction, but that's only associated with the noise in the data. But here we are looking at actually the uncertainty associated with the lack of sample. So this correlation function is based on the spatial relationship between the data. When the data is far apart, there's a lot more uncertainty, which means you can add more sample to improve your accuracy. So the GP model is useful for on-demand simulation, for data fusion from, bringing data, integrating data from both simulation and experiments. It's also very useful for the digital twin concept when you have the operational data comes in. And it is useful for uncertainty propagation to create a model, surrogate model that can pass through micro, meso to macro analysis. And in this case, we also demonstrate that the GP model can be used to model non-stationary spatial variation. So for this example is a woven composite. We actually model the uncertainty of the volume fraction, the uncertainty of the fiber angle. And with the nested uncertainty propagation at the end, we demonstrate that we're able to assess the mean in terms of the performance here. This is the force displacement curve, right? And you can see the uncertainty that's 90% confidence interval. And as well as showing here in this small specimen is the mean value as well as the variance, the uncertainty associated with that. And this is only for linear behavior, and it has a huge potential to be extended to assess the uncertainty for nonlinear behavior, which is more critical. The GP model is also very powerful to be integrated with like a Bayesian optimization. So here I try to use this diagram to demonstrate the concept of Bayesian optimization to do global optimization. So the idea is that you have a GP model and uncertainty quantification. And in Bayesian optimization, you have an acquisition function that balances the need for exploration to reduce the uncertainty, as well as for exploitation is that for optimization. So the acquisition function make trade-off between these two aspects, and each iteration you add one or more points, and you continuously update this Gaussian process model and for optimization purpose. And this method is extremely useful for capture the solution for very nonlinear problem. But on the other hand, the current method can be used for continuous problem. But in material design problem, we have many situations that not only we have continuous variable, but we have category variable like chemistry element, surface treatment method, and we call them T here. And X are the continuous variables. So how do we build a GP model to quantify the uncertainty? The traditional work, the GP model takes into account the spatial correlation. So you really have the distance, right, measure the distance between different design options. But here, when we have category variable, it becomes difficult. How do we measure the distances, right? If we think about, any physical behavior underneath any category concept, there are always quantitative variable space. So in traditional machine learning, a person or an analyst have to come up with descriptors, right? It could be very high dimensional as inputs. Our idea here is to bypass those arbitrary choice of descriptors. Instead, we create a latent space called a Z. It's a very low dimensional latent space. We found that in many cases, 2 dimension is quite sufficient. And in this latent space, we capture the distances between different category variables. So if you think about the traditional GP model, use the Gaussian process function. And here we do a a small modification. In addition to find the hyperparameter for this correlation function, we are adding z as additional variables. So for optimize the maximum likelihood function, we're not only find the hyperparameter, we also try to identify the location of the latent variables. Once the location is identified, it helps us to achieve an implicit mapping between categorical variable and the numerical value. It provides a physics-based dimension reduction, because here those distance actually is not only in the latence, is not only in the input variable space, it takes into account their impact on the property of interest. So it is a physics-based representation, tell us how this concept is different in terms of the impact on the property of performance. And finally, because it's a GP-based method, the uncertainty quantification also allow us to achieve like a data fusion and the Bayesian optimization, as I have explained earlier. So we actually have tested this method for different material design problem. And here I will just quickly show two examples that happen to be both published as a review article in the journal, two journal. One is the Molecular System Design Journal, another one is the Applied Physics Journal. So one is nanocomposite design. Here the problem is, in addition to design the morphology, which can be represented by the spectral density function, we're also designing the choice of polymers as well as the choice of surface treatment. So these are all categorical variables, but at the end, our solution converge to both the morphological design as well as the discrete variable design. Another example is a APAE project for microelectronics design. So here is the problem that we're looking at a very combinatorial search problem that each of this element have many different choice. So we found that using only 7% computation of the whole possible combinations, we're able to find the optimum solution. Again, the behavior like the band gap and stability is very highly nonlinear. This is example to show that we actually can visualize the latent space for each of those categorical variable. We plot the relative position of the material, the chemistry element. So when the chemistry elements are very close to each other, means they have very similar behavior impact on the property. And it's interesting to see some of them actually can be explained by the proximity, how close they are in the chemistry table. But some of them cannot, because the very complex coupled effect, the physical phenomenon here is very complex. We actually use DFT simulation that each simulation can take days. And with this, I want to move to the topic of design synthesis. So what I want to show you is that some of those data-driven machine learning technique, like LVGP method, could actually benefit very large-scale, multi-scale design problem. I'm not going to explain what is exactly metamaterial design. I think a lot of people are very familiar with this concept across fields of mechanical as well, optical, and many other fields. So it could be a multi-physics kind of phenomenon. But I'm using this butterfly example just to show that our vision is to design a system, not only the shape of the butterfly, but also at each location, we can choose different material. So it could be a very heterogeneous system and also different microstructure design. So it's a multi-scale design problem that involves a lot of combination, very high dimensional. And in the topology optimization area, people are actually looking for like multi-scale topology optimization methods. But on the other hand, many existing methods, you have to assume the material is the same everywhere. So you cannot change material definition or the unit cell design. So we are proposing a new framework, a data-driven framework. In this framework, we start with creating a large database, and then we do machine learning to achieve mechanics-based learning, understanding. And then we do, at the end, we use a data-driven approach to synthesize those different concept unit cell at the system level and to make sure that they're very well connected to achieve the overall system performance. So going back to the LVGP method I discussed earlier, I'm showing you here that it could be a very powerful approach to accomplish such a multi-scale design. So here the categorical variable can be associated with different type of or class of different unit cell. And this is a lattice type. You can choose different type. On the other hand, the quantitative variable could be volume fraction or material property. And using the latent space representation, here we're doing multi-space LVGP and the multi-response associated with the property in the stiffness matrix, like C11, C22, and so on. And once we create a database, either it will be like a 3D or 2D, we actually can use latent space to achieve a new understanding of physical interpretation. For example, this one shows that in the 2D space, you can see that the cubical symmetrical geometry are clustered on one side, and on the other hand, we can see that some other also tropic materials are at the edge. And this similar observation can be made for the 3D structure, like center and outside, they have very different structure. So we're using the LVGP, and now with the database, well, with the LVGP model as a surrogate model, our computational efficiency is equivalent to a single scale topology optimization. So I'm showing you here a kind of academic example, like L-shaped design that you can benefit from choosing different unit cell at different locations. On the other hand, this is a compliant mechanism design that you try to optimize the largest displacement. So here we use two different type of material, the stiff material and the soft material. And this paper actually it's being published in this year's IDTC conference. That this is a very large, exploration, but we're able to do this very efficiently using the database we have. We can work with the very regular, like a lattice type of structure, which could be very nice from the manufacturability point of view. On the other hand, we can also open this up to unit cell design or database, which we call the free-form geometry. So this is a paper we published, the special issue of AI in the CMME journal, that we actually create a 250,000 samples that we can use a VAE model and adding a regression layer. So the encoder layer derives the latent variable, and then the regressor maps the latent variable to the property space. And this model is very flexible, actually allow you to do both prediction as well as inverse design. So given any target property, now you can find out what is the corresponding unit cell. And using this database, we used a two-level design approach that first identify using topology optimization to identify the optimal property, and then search the database to assemble them together using we call a tiling optimization algorithm. I'm not going to go into details of this algorithm. It's published in this paper that you can take a close look. But this is a smiley face like example, right? You could actually use this one to accomplish the desired distortion. So when you apply the road, it can change from a crying face to a smiley face. And here are a few more examples that you can see that we can use aperiodic microstructure design at a different location, different unit cell to accomplish very different distortion behavior. And recently, this work is being actually reviewed right now. We're using this method to achieve what we call the string clock. So string clock is a method that you can actually conceal object within the string field of homogeneous surroundings. So if you imagine that this is a structure with the unit cell repeated everywhere, and this is the string, like a displacement field. After you put a project in the middle, right, without cloaking, you can see that the displacement field will be very different. What we want to accomplish is that we want to design this cloaking region, including its boundary, through topology optimization, and then we can accomplish the same displacement field. So there's no change after you place the object inside. The existing methods are very limited, and I think in general for mechanical cloaking is a much more difficult problem than optical cloaking problem. So using our approach in collaboration with Cartech, Kara DeRio's group, you can see here we did a physical validation. This is a fabricated 3D structure that we demonstrated that the simulation results with cloaking, without cloaking, you can see that the physical experiments accomplished very well. So there are very obvious cloaking effect accomplished by the physical specimen. So just a very quick show, a movie show here of we are able to take into account very different voids with different shapes. And also we are able to either fix the cloaking region or design the cloaking region as a topology optimization problem. So here we not only design the boundary, but also design the target property and different locations. We can also use this method to easily handle very complex objects, like a butterfly that has two voids rather than a single void. I can tell you that many existing methods cannot accomplish that. And I am adding another example to show the benefits of aperiodic design, the data-driven approach. So you can see here that using the method I'm presented, we can actually design a structure, aperiodic structure, with much better fracture resistance. So this is a purple curve that you can see that this has a similar strain value, accomplished strain value, but much better toughness because the surface area under this is much higher than the aperiodic design, either A or B. So with that, I'd like to summarize my talk today. I covered these 3 different subjects, and basically the takeaway is that stochasticity really plays a critical role in material behavior modeling, and this is a very design of material system is a very interdisciplinary field that design mechanics, material manufacturing are highly coupled. And we have methods that can handle both big design problem or small design problem. We need methods for that. And I demonstrated that the Gaussian process model provides a lot of flexibility in machine learning discovery as well as design. On the other hand, the sophisticated method can handle, machine learning technique can handle very complex phenomenon, and with accelerated physics modeling at runtime, as well as multiscale, and as well as modeling multiscale and the heterogeneous behavior. What I haven't shown you today are some of the systems that we have been thinking about, or the community, the large community of topology optimization. You will see more talks throughout the conference. You will see some keynote talks on topology optimization that try to address, for example, nonlinear behavior. That could be either geometrical or like material-based nonlinear, and systems such as very heterogeneous, like this one, the composite system can be serve multiple functions such as thermal protection, shock, like absorption using different process technique. A multi-stable state metamaterial is a very tough problem because that you have to handle both, buckling, post-buckling behavior, which create non-linear, discrete actually phenomenon. Most of our method can only model continuous phenomenon. And active metamaterial adds another dimension of complexity. Now you're not only designing the material structure, but you're also designing external force like heat or electronic, wave and things like that. So those problems have been, looked at by many other people, and I think there's a potential of using data-driven methods for that. And with that, I really like to acknowledge the support from many different funding agents throughout the years, and my students' work, which really makes it possible to put all these things together in a systematic way. Each of them are tackling a different aspect. So with that, I like to open for any questions. Thank you very much.
Thank you. Such a nice and entertaining lecture. Before I ask a question, I remind the audience that there is a button on the left-hand side. At the left sidebar, you can click on Professor Wei Chen's name and type in your questions. Wei, I have 2 questions for you. The first question would be, I'm very interested in doing topological optimization in manufacturing. Now, but before you do manufacturing, you do not really know the material properties because the process will change, right? But at the same time, your topological optimization algorithm, whether it's a composite or additive manufacturing, you do not really know the material properties, and also you do not really know whether there's damage inside the processing. So how are you going to handle this problem in design? Yeah,
so you ask the most tough problem that I would think it's not solved. But the community, the structural optimization community are working towards the goal. The issue, as you said, it's more like a chicken egg thing, or it's in the computational process, it's iterative, right? Topology optimization need to know the material definition, right? On the other hand, that is also influenced by the process, but then the process also need to know the geometry in order to correctly simulate the property at different locations, right? So we have seen some work that kind of not using the full process simulation, but try to define the thermal paths or the changing behavior throughout the part and use that and integrate that as positive topology optimization. So I think George Olaire and some other groups, they're working on integrating thermal models into topology optimization. But I think those work, I feel the whole community is still at the very early stage of that part due to this iterative nature, unless if we change the algorithm, the TO algorithm fundamentally. I think that's a challenge there.
Okay, that brings me to the second question. So you are talking about multi-physics, multiscale. So you do have a curse of dimensionality, right?
Yes, yes.
So how you actually, using machine learning to reduce all this computation so that it's feasible? Because I read the latest paper from Nature about what's the limitation of a single physics design.
Yeah.
And they have a limitation already. Okay.
Yeah.
So how are you going to do that?
Yeah. So the challenge of multi-physics, actually, it is more towards how do you calculate the gradient information. So it's a little bit different story from the multiscale. Multiscale actually is the area I think the data-driven method can play a great role. Like what I showed in my talk, we can use like LVGP model or some other model to surrogate the nonlinear or linear behavior, the material law. And then the multi-scale problem becomes the single scale. We can use the single scale like efficiency to solve multi-scale problem.
Okay, so there's a quick question along this line. There's a question from Susanta Ghosh. They ask you, can you please comment on the efficiency of the latent space, Gaussian process approach for runtime use, especially when the number of data points used to train the GP are very large?
Yeah, so I think the question is more towards if GP is applicable for large data set. Because traditionally GP model is more suited for small data. We actually have a paper being published this year in the IDTC conference is how do we deal with large data set. We use statistical variation approach first to reduce the large data sets to 1,000 or even more to a small set, but the representative, of the whole space, and then use those data to fit the GP model. So I think, and the GP efficiency can also be improved using some other numerical methods. So the answer is, I think runtime GP modeling is very much possible these days.
Okay, thank you very much, Professor Wei Chen. And again, thanks again, the very enlightening lecture. Thank you.
Thank you, everyone.